Good morning, Mr. Kwok. I am Nishta Khanna from class PE04, and today I will be discussing on my device the electroencephalograph, commonly known as the EEG. The electroencephalograph or EEG machine, originating from Hans Berger's pioneering work in 1924 and further advanced by William Gray Walter's discoveries of delta waves in 1937, represents a cornerstone in neuroscience. By measuring electrical potentials across the scalp using electrode pairs and translating them into fluctuating waveforms on a monitor, EEG technology offers invaluable insights into brain function. These insights are particularly vital in diagnosing and monitoring conditions like epilepsy, showcasing the significance of EEG in understanding the human brain. The construction of the EEG entails several key components. Small metal electrodes, typically made of silver or silver chloride and shaped as cups, discs, or needles, are placed on the scalp and secured using paste. Occasionally, conductive gel is utilized to improve the electrical contact between the electrodes and the scalp, enhancing the accuracy of brain activity measurement. Signals captured by the electrodes undergo amplification via a differential amplifier and filtering to remove unwanted noise. Finally, a computer control module processes the amplified signals and the resulting data is displayed on a monitor or can be printed for further analysis. The primary function of the EEG is to measure variations in electrical potentials recorded using scalp electrodes, reflecting the electrical activity on the surface of the brain, specifically the cerebral cortex. It provides a physiological assessment of cerebral activity. Key characteristics of EEG recordings include a frequency range of 0.5 Hz to 30 Hz and a maximum amplitude of 100 micro VPP. EEG measurements employ two main techniques. Firstly, the monopolar technique, which uses one active recording electrode placed on the area of interest, a reference electrode in an inactive area, and a ground. The bipolar technique involves two active electrodes on the area of interest. EEG measures brainwaves through electrodes by summing up many action potentials sent by neurons in the brain. The applications of EEG encompass a wide range of neurological assessment and diagnostic capabilities. These include the physiological assessment of cerebral activity, aiding in the diagnosis and evaluation of various conditions such as epilepsy, coma, organic brain syndrome, sleep disorders, and dementia. Additionally, EEG plays a crucial role in determining brain death, monitoring brain function in intensive care units, and detecting non-convulsive seizures and status epilepticus. It also utilized to assess the effect of anesthesia in medically induced coma patients and to monitor for secondary brain damage in conditions like hemorrhage. Moreover, EEG is valuable in identifying the presence of lesions, brain tumors, and sleep staging. When it comes to problems associated with the EEG, firstly, the frequent use of wet electrodes in EEG testing leads to mechanical injury during skin preparation, prolonged pressure from electrodes, and chemical irritation from conductive paste. This discomfort can manifest as an uncomfortable and itchy sensation for users, impacting the overall testing experience. Secondly, commercial EEG systems commonly used in clinics or hospitals lack portability. This lack of portability poses a significant inconvenience for patients who may not have the time for long EEG tests, hence restricting their accessibility and potentially delaying crucial diagnostic procedures. The third problem is that patients experience user discomfort during long EEG tests due to the presence of multiple wires. This makes it challenging for patients to sleep during the EEG test and ultimately affects the overall testing experience. Lastly, EEG suffers from the presence of motion artifacts caused by physical movements of the subject, such as eye blinking, glances to the left or right, or movements of the neck or jaw muscles. These artifacts greatly impact the accuracy and reliability of EEG signals, posing a significant challenge for accurate diagnosis and monitoring. Delving deeper into problem 1, which is electrodes used in EEG monitoring frequently lead to skin irritation, hence presenting significant challenges for patients undergoing monitoring. Mechanical injury can occur during the skin preparation process, which involves removing layers of scalp epidermis and due to prolonged direct pressure from the electrodes on the head. Additionally, chemical injury may result from conductive agents applied during electrode placement, leading to contact dermatitis. The severity of skin irritation can range from erythema to skin breakdown or even skin ulcers. Previous reports indicate up to 81.7% of EEG electrode-related skin irritation from patients. The third problem is user discomfort due to many wires used in EEG procedures. Challenges in remaining still and avoiding excessive motion due to numerous attached wires leads to user discomfort. Many patients are usually advised to avoid wires from being too far from the scalp during the test, which can make the patient feel cramped and uneasy. Many surveys indicate of electrodes falling off overnight, contributing to an overall uncomfortable procedure. When it comes to patient response, there are many instances of patients removing the electrodes due to discomfort. A study conducted for EEG tests revealed that participants reported increased discomfort after approximately 25 minutes. Lastly, motion artifacts influenced by body and device movements pose a significant challenge in EEG recordings. Eye blinks are identified by strong negative signals in the frontal part of the brain. This is known as Bell's phenomenon, which occurs because the cornea and retina produce positive signals during blinking. Additionally, lateral eye movements generate opposite signals in specific brain regions due to differences in charge between the cornea and retina. Furthermore, rapid bursts of activity during chewing and tongue movements, often mistaken for muscle artifacts, require careful distinction. Such movements disrupt the electrode-skin interface, known as ESI, resulting in distortions in EEG recordings. Variations in ESI impedance directly impact the amplitude of the output signals, as indicated by the voltage gain formula shown above. Hence, this leads to distortion and affects the output signal. To tackle the listed problems, I have come up with a few solutions. The first solution is a wireless EEG ear headset, which aims to address the discomfort associated with multiple wires during EEG tests. It replaces conventional wires with secure probes, ensuring freedom of movement and reducing concerns about accidental pulls. It features a lightweight and portable design with probes extending from ear covers, hence improving overall portability and providing a seamless testing experience. This advancement revolutionizes EEG tests, making them more user-friendly and comfortable. Its features are ear covers. These are the parts of the headset where the sensors or probes extend from. They're made of a waterproof material called silicone. Their design contributes to the headset's lightness, making it comfortable for users to wear for long periods. They also enhance portability, allowing users to easily carry and use the headset in different places. The ear covers enable users to sleep comfortably on their back without any discomfort and provide users with the freedom to move around during various activities. The sensors/probes are components which replace the traditional wires in the headset. They're designed to be rigid, ensuring that they stay securely in place during testing. This rigidity also helps minimize interference during the collection of data. The next component are electrodes. The electrodes are located at specific positions on the scalp following the 1020 International System. They are made of a dry electrodes, specifically silver chloride electrodes, which simplifies setup by eliminating the need for conductive gel or paste. This enhances user convenience and reduces preparation time. The benefit of this is that silver chloride polarized electrodes also act as a low-frequency filter, reducing interference from patient movement, muscle artifacts, and electrical equipment, hence enhancing EEG recording. Lastly, there is a band at the back of the headset. It serves a dual functionality. It secures the device in place and also provides additional comfort. The band ensures headset stability during prolonged use, contributing to consistent and reliable data recording. Here is a 3D model of the headset from different views. The proposed wireless EEG ear headset offers an innovative solution to discomfort associated with traditional wired setups. By replacing the wires with secure probes, it ensures enhanced user comfort during EEG tests. The design featuring silicone waterproof ear covers prioritizes lightness for extended wear and portability. The rigid sensors guarantee secure placement, minimizing interference during data collection. The dry electrode technology simplifies the setup by eliminating the need for conductive gels. Additionally, a stability band at the back ensures consistent and reliable data recording. Hence, this solution effectively addresses user discomfort, promoting a comfortable testing experience and enhancing EEG system portability. The second solution are skin electrodes. Skin electrodes are known for their stretchability, skin conformity, and biocompatibility. They serve as crucial interfaces between the body and electronic devices, facilitating the skin electrodes. The second solution are skin electrodes for their stretchability, skin conformity, and biocompatibility. They come available in wet, dry, and semi-dry forms. These electrodes are strategically placed on the skin surface to accurately capture signals, hence alleviating skin irritation by eliminating the need for conductive gels, ensuring user comfort, and making monitoring sessions safer and more tolerable. These are the components of the skin electrode. The ultra-thin dry epidermal electrode, only 100 nanometers thick, adheres tightly to the skin, ensuring precise data capture with minimal resistance, and impressive stretchability of over 400% for accurate measurements during movement. Its skin-like flexibility and thinness creates a comfortable interface, enhancing signal quality by reducing impedance and increasing signal-to-noise ratio. Thirdly, conforming closely to the skin, the electrodes provide a comfortable interface by managing skin moisture for optimal capacitance and resistance. They offer performance comparable to, if not better than traditional electrodes, especially in capturing high-quality signals. Skin electrodes offer numerous benefits, notably reducing skin irritation commonly associated with traditional electrodes by eliminating the need for conductive gels. Their breathable design facilitates the dissipation of epidermal. Last but not least, solution 3 is a wireless in-ear EEG recording. These compact devices provide portability for everyday use and ensure a secure fit, minimizing motion artifacts and electromagnetic interference. Compact and lightweight design, lightweight materials are used such as memory foam, silver-coated cloth for enhanced portability. For firm electrode placement, electrodes integrated into the earpiece for direct contact with the ear canal ensures secure and stable placement to minimize motion artifacts. We also use conductive materials such as gold, silver, and conductive fabrics for optimized electrode conductivity and to reduce impedance for improved signal quality. For advanced signal processing, there is an implementation of signal processing algorithms for motion artifact removal, such as adaptive filtering, blind source separation, and machine learning. The last one is low-profile design, a minimized profile to reduce external forces impact on the device. This leads to a lower likelihood of displacement during head movement. In conclusion, the in-ear EEG device minimizes motion artifacts artifacts by utilizing a compact, lightweight design with memory foam and conductive materials like silver-coated cloth. Firm electrode placement directly in the ear canal ensures stability. Integration with Bluetooth earphones enhances user convenience and stability during motion, while wireless connectivity eliminates wire-related artifacts. Advanced signal processing algorithms, including adaptive filtering and blind source separation, effectively remove motion artifacts. Also, its low-profile design reduces external forces impact, ensuring stable EEG signal acquisition during head movements. Overall, the device combines ergonomic design, conductive materials, seamless integration with wearables, wireless connectivity, and advanced signal processing to mitigate motion artifacts. Here are some recommendations which can enhance the functionality of the EEG system. Implementing a silver chloride electrode to act as a low-frequency filter reduces interference from patient movement, muscle artifacts, and electrical equipment, thereby enhancing the EEG recording reliability and accuracy. Secondly, opt for cup-shaped electrodes for improved adherence to the scalp, providing better stability during EEG recordings. The next part is Introduction to Good Practices. GMP, or Good Manufacturing Practice, for medical devices refers to quality assurance standards and guidelines that ensure the consistent production, testing, and distribution of safe, effective medical devices. It encompasses design, manufacturing, quality control, and documentation processes. Standards play a pivotal role in maintaining consistency in essential features of goods and services, ensuring they are fit for their intended purpose. ISO 14971, 9001, 13485, and the IEC 61010 series are examples of basic standards used to ensure the medical device's compliance to regulatory requirements. Now we will move on to good practices in design. EEG machines designed with good practices ensure precise recording of brain signals, aiding in diagnosing conditions like epilepsy, sleep disorders, and brain injuries. Here are some examples of good design practices. Firstly, understanding user needs and requirements. This is a crucial step in medical device design, as the information collected is essential for creating a medical device that is safe, effective, and seamlessly integrates into the user's life. The manufacturer must conduct thorough research through methods like in-user interviews, surveys, and observations to gain insights. Secondly, understanding the device. Understanding the EEG's primary function of capturing accurate and reliable brain signals is essential for precisely collecting data. By prioritizing this core functionality, designers can improve their device's overall performance and utility for users. Lastly, ensuring the design EEG conforms to rules and regulations. Regulatory compliance guarantees that the EEG device meets established standards and guidelines set by the authorities, ensuring its safety, reliability, and performance, hence facilitating market access. Now we move on to good practices in maintenance. Regular maintenance ensures accurate EEG recordings, aiding in accurate diagnosis and treatment decisions. Here are some examples. First of all, sanitization and cleaning. To avoid the accumulation of dirt and bacteria, it is essential to regularly clean and sanitize the electrodes, wires, leads, and external surfaces of the EEG equipment. You must also examine the leads and cables. During recordings, low signal quality may be caused by damaged cables or leads. Hence, frequent inspection assists in the early detection of problems, enabling prompt intervention. Thirdly, the changing of batteries. Regular battery maintenance is crucial for EEG equipment that are portable or battery operated. Lastly, changing the electrogel. Over time, electrogel used in EEG recordings may dry out or lose its ability to conduct signals. Hence, replacing the electrogel on a regular basis guarantees the best possible signal quality.
Recommendation 1. Regular calibration and remote monitoring. Implement automated calibration reminders to optimize EEG equipment and integrate remote monitoring for quicker issue resolution during sessions. Recommendation 2. User training programs. Develop comprehensive courses covering EEG functionality and maintenance, include hands-on practice sessions in simulated environments, offer ongoing education modules on EEG technology and maintenance best practices. Lastly, conduct frequent training sessions to maintain user proficiency.
Lastly, a maintenance checklist is needed to ensure consistency, prevent oversights, track maintenance history, demonstrate compliance with regulatory requirements, and optimize efficiency during equipment maintenance routines. This checklist contains 16 of the most common maintenance practices for EEG. It spans from sanitation, cleanliness, to component and electrical checks. In summary, the presentation covers all essential aspects of EEG devices, starting with a comprehensive description. It outlines the construction details, functionality, and applications of the devices, providing clarity on their purpose and use. Safety issues associated with EEG devices are then addressed, highlighting potential problems such as discomfort, skin irritation, and etc. Discussions surrounding these issues are accompanied by possible solutions to mitigate risks effectively. Lastly, the presentation emphasizes good practices in design, maintenance, and it delves into the importance of adhering to these practices, providing recommendations. Lastly, a checklist of good maintenance practices is created to assist users in implementing these recommendations systematically. We have come to the end of the presentation. Thank you.